Hello everyone, this video could be fun for those of you who are interested in the formalities of probability or formal statistics, probability theory, or mathematical economics as well. What is a sigma field? Groups, rings, fields. Sigma fields are kind of an interesting thing that lives in a strange place in probability and statistics because if you've ever taken an upper level, kind of formal probability or statistics class, there's a very good chance that you saw these things right at the start of the class, sigma fields, defined as where we are going to define probability itself. And we have this nice formal explanation for what a sigma field is and how probability is defined on a sigma field, and then that tends to disappear. Basically, after the first week of class, you start doing real statistics and talking about distributions and all of the rest. Well, it's the same if you ever look in a textbook on probability or statistics or things like forecasting, which I teach. Sigma fields pop up at the very beginning in a formal definition of what probability is and why probability theory is rooted in mathematics, so that we can say that statistics is actually a branch of mathematics, which is a little bit contentious. But the concept of a sigma field being a field is rooted in the idea of what a field is in formal mathematics. And so if you don't have a formal pure math background for things like group theory, ring theory, field theory, then the idea of a sigma field is just a thing with an esoteric name, even though sigma fields tend to have operations that just look like logic and they make sense, talking about a coin toss either being heads or tails or perhaps both, but never both. Um, we're going to do that one here in a second. Group theory, ring theory, field theory would be the background for this that you don't normally get in a probability or statistics course. And so if you only have the flavor of a sigma field that you pick up from a probability or statistics course, I'm going to give you some of the background on the pure math side for what those things are, why they kind of look like fields, although they are a little bit different from proper fields. So that's why we've got a different name for them. You don't normally see these things together in the same list. As I just said, groups, rings, fields are a pure math concept, and sigma fields are usually introduced in the context of probability and probability spaces. But we're going to build it up from group theory and then go through from there. So all of these are just sets. Okay, sets with properties that behave how we think they should. Specifically, a field. A field is a set that is kind of the deluxe version of all of this. It's a set that has all of the properties that you know and love from things like real number line. Well, guess what? The real numbers are a field. So we're going to work up to that. And sigma fields are basically fields of sets, as it says here, a field of sets more or less. We will define events, things that either do or don't happen. The events can sometimes include more than one of what we might call outcomes. If I roll a die, a six-sided die can be 1, 2, 3, 4, 5, or 6. And I could define an event, say, what is the probability that the die comes up 1 or 2? Or 2. Okay, so now I've added some things there. Or I could say, what is the probability that it comes up with an even number? Okay, so I can define events that are a bigger set, a bigger space than just the 1, 2, 3, 4, 5, and 6 that I have on the sides of the die. That's going to be a sigma field. By the way, field and algebra in this context are two words that are used interchangeably. So even if there's a slight technical definition and difference in terms of how you might define a field versus an algebra, they more or less implement the same ideas. So a sigma field, single sigma algebra are going to be the same idea. We'll use those terms interchangeably. We'll start off with a group, then a ring, and then a field, the deluxe version of a set with operations. Very nice. Before we do a group, we should probably just talk about what a set is. Of course, a set is a collection of objects. The objects in the set are called elements of the set. Okay, a set could be anything. I'll start with the simplest thing that I could possibly have. Right here is the empty set. Sometimes we call it the null set. It's got nothing in it. It's empty. So I've got my curly brackets here to say, here's all of the stuff that's in my set. And as you see, there's nothing. You get nothing, and you're going to like it. The next one, I just made up a name for it. Let's call it A. It's a set. A is the set 1, 3, 5. Okay, so I just talked about what's the probability that a six-sided die comes up with an even number. Suppose that it comes up with an odd number. These would be the three things that it could be. It could be a 1, a 3, or a 5. Simple enough set. I see that it has 3 elements. I could compose some combinations of those elements and define events, but it's just a set. Or north-south. Easy peasy. This is a set of 2 things. It could be north, it could be south. Looking at a map, you might add east and west, and then you've got a more interesting set that would have 4 elements. We can define operations on these sets. So I can say, if you give me an element of that set, I can define the complement to that element. Or if you give me a subset of that set, I can define a complement to that subset. So I'll define the complement of x. By the way, x, I could write a set here instead of just a thing. The complement of a thing. Okay, so for A, the complement of this set 1 would be every element in A, such that that element, x is being used as a variable here, right? Every x, every element in A, such that that element is not in the set I defined over here, which was just 1. Okay, and I go back and I look at A, and I say A had 1, 3, and 5 in it, so the set of all of the things here that aren't 1 is just 3 and 5. If I define the complement to 1 and 3, the set of everything in here that isn't 1 or 3, would be 5. And complement is very, very easy. Just an example of an operation. Operations like the complement can have different properties. Those properties are going to be important when we talk about how this thing builds out into a bigger set with nice operations that do the things that you want them to do, like math usually works on the real number line: addition, subtraction, multiplication, division. Please excuse my dear Aunt Sally, those sort of things. So let's define some properties for operations. An operation, which I'm going to call star. This could be anything. If you like, make it a plus, and we'll call it addition. All right, but it could be anything. It could be multiplication or division. An operation is closed if, for any x and y in the original set, x star y is also in that set. That just means that this operation, notice that it takes 2 arguments. I've got x and y, and x star y is how I write x being operated with y, x star y. Not necessarily the same as y star x. More on that in a minute. But x star y is going to produce some answer, some result. If that result is in the original set that you started with, then we call this a closed operation. If it's always in that set, I should clarify. You can imagine operations that don't stay in the set where you started. So, for instance, if I take integers, 1 divided by 4 is a quarter. That's not an integer. It's a real number. It's a rational number, but it's not an integer. So we'll keep that division in mind as something that maybe is not closed for integers. How about this one? Matrix multiplication is really interesting. You can do matrix multiplication with matrices that are not square. If I talk about 2 by 3 matrices, and I define multiplication as, transposing one of them and then multiplying, the result will either be 2 by 2 or 3 by 3. So 2 by 3 matrices, even though matrix multiplication works just fine, it's going to map those matrices into something that is not a 2 by 3 matrix, so it's not closed. On the other hand, addition for integers or rational numbers or real numbers is going to be closed. You're just going to get another number back from the same family. Okay, an operation is commutative if, for any x and y in the original set where you were, x star y, I didn't get my curly s here, x star y is equal to y star x. Okay, that's commutative. If you can do it either way and get the same result, then you're happy. Again, the matrix multiplication with non-square matrices is not going to be commutative. How about associative? This is the one with the parentheses, if you're trying to keep these straight. The associative property says that an operation is associative if for any x, y, and z in S, x star y star z in parentheses is equal to x star y star z with the x star y in parentheses. So I can move the parentheses, meaning it kind of doesn't matter which order you do these in. 1 plus 3 plus 5 should give me the same answer, 9, as 1 plus, parentheses, 3 plus 5. Doesn't matter where you put the parentheses, it's gonna work.
It doesn't work for every operation, though. And again, we could think about things like multiplication or division or subtraction. Subtraction is very strange. We can break these. But closed, commutative, associative, these are nice operation properties that we might want to have. Example, natural numbers. Okay, so natural numbers, think of the counting numbers not including zero. I'm noting here with the subscript that I'm not including zero. Zero is very special. So I'm ignoring it for now. And you can debate whether we call these natural numbers when we don't include zero. Nobody knows. Everybody argues over that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Keep going as long as you want. Addition. This thing is closed under addition. So 1 plus 2 is 3, which is also a natural number. 1 plus 5 is 6, which is also a natural number. This is only going to map to other natural numbers, other integers on the right, further on the number line when I take two elements together and add them together. And it's kind of a fun proof to try to prove that two elements of this set added to each other are another element of this set. That would be a fun thing in an upper level kind of formal math class to prove some of these operations are indeed closed, or see how much else you can prove using these simple definitions. So addition is closed. Easy. Subtraction is not. Subtraction is quite an interesting thing. I often joke that subtraction is just evil addition, because it is. You take addition, and if you can invent some sort of an additive inverse for a number, a negative version of that number, hey, that's what subtraction is. Subtraction is defined as adding the negative version of that number. I don't have negative numbers in my set of natural numbers with or without zero. So I can't really define it that way, but I can define it as something that just looks like subtraction that I know and love because we've been doing it since we were little kids. And it's fine, but it's not closed. If x is equal to y, and I try to subtract x from y, I'm going to get 0 if these two numbers are the same. And in that case, it doesn't matter which way you do it. X minus y is equal to y minus x. You're going to get 0 because x is equal to y. 0 is not in this set. Okay, well, 1 minus 5 we normally think of as being negative 4, which it is. Negative 4 is not in this set, so it's not closed under subtraction. As for commutativity and associativity, addition is commutative in this set. 5 plus 6 is equal to 6 plus 5. No problem. Subtraction is not going to work that way. 5 minus 6 is minus 1. 6 minus 5 is positive 1. So they're sort of like opposite numbers. Very different. And associativity? Well, addition is fine, but again, subtraction is not okay with associativity. If I say 5 minus, parentheses, 3 minus 3, the 3 minus 3 is 0, and I just get 5 over here. If I say 5 minus 3, okay, so I got 2 here, and then I subtract 3, it takes me down to minus 1. So very, very different for subtraction, depending on where you put the parentheses. I see. Okay. If it was addition, I'd be fine. It wouldn't make a difference. So these properties matter. We'll define a group based on those properties that I just listed, which were all pretty straightforward. A group G is a set with an operation. It could be star, it could be addition, it could be subtraction, it could be multiplication would be fun. A group is a set with an operation such that that operation must satisfy. It needs to be closed, okay? It needs to be associative, and the special one, there has to be an element in G such that I times x is equal to x times I. We'll call this element here, and I just said times. I star x is equal to x star I is equal to x for every x in G. Every x, what do we call this element? Because x star I is just x, or I star x is just x, we're going to call this the identity element with respect to this operation star whatever it might be. The identity element for addition, fairly easy, is 0. If I take a number and I add 0 to it, I get the original number back. If I take 0 and I add a number to it, I get that number back. So we're going to call this the additive identity element if star is addition. For multiplication, you multiply a number by 1 and you get the original number back. You multiply 1 by a number and you get that number back. Easy peasy. So The identity element for addition is 0. The identity element for multiplication is 1. But there needs to be an element like that for whatever operation it is that you're thinking about in order to call it a group. And for every x in G, there needs to be an element y, another element, not necessarily the identity element, such that x star y is equal to y star x is equal to the identity element. We're going to call y the inverse of x under this operation star. Okay, so the additive inverse of 5 is negative 5. If you add minus 5 to 5, you get 0, which was the additive identity element. So that's fairly straightforward. With multiplication, the inverse of a number would be like the multiplicative inverse of 5 in order to multiply by 5 and get 1 back, because that was the identity element with multiplication, I need 1 over 5. So multiplying by the multiplicative inverse is basically division. Okay, it's undoing that thing that you just did in order to return the identity element. This is why I joke that subtraction is just evil addition and division is just evil multiplication, because it's really undoing that addition or multiplication, whichever you were starting with. Okay, and the same thing here for this hypothetical operation. Star, I just have an inverse element for every element in G. We're building up a nice set of properties here. So star is starting to look like or act like something like addition or multiplication in terms of how those things look and act in the real numbers, which we know and love. Not so bad. Okay. Now the identity element here, okay, for the natural numbers without 0, it's closed, it's commutative, it is associative with addition, all right? X plus I is not equal to X for any I in that set, because the I that would be the additive identity element is 0. The exclamation point here, by the way, is not 0 factorial. I mean 0 exclamation mark. That's the additive identity element, and it's not in this set because I specifically ruled it out and said we're not including 0 here. All right? Well, what about this? X plus y equals 0. How would I find an element here where x plus y is equal to 0 in order to have an additive inverse? Well, in just these positive counting numbers, you're not going to have anything like that. You're going to need some negative numbers in order for this to work with addition. So no, these natural numbers excluding 0, call them counting numbers if you want, they're not a group by the formal definition with addition. But if I allow 0, and if I allow negative numbers so that I can have that inverse, first of all, if I allow 0, then I have the identity element with respect to addition. That gets me half of the way, right? That gets me property 3 here. If I allow negative numbers, and I talk about z, the integers here, well then I have my additive identity and I have my additive inverse. So I get 3 and 4. This is a group with respect to addition. It does all of the regular things. You have addition, you have inverse addition, which we can call subtraction if you want, and addition and subtraction. Hey, that's great. And then you might think about trying to build this a little bit more, adding some more properties. Talk about multiplication, talk about division, talk about anything you like. But we've got a group here, so that is not bad at all. I think we can take this thing to the next level. There's a special type of group. Because the definition we had a moment ago does not strictly require commutativity, but commutativity where x star y is equal to y star x all of the time, that seems like a useful thing to have. And of course, addition in the integers does have that property, so I might ask for commutativity back, if you're willing to give it to me. And we'll call the group an abelian group, or just a commutative group, if commutativity holds for all elements. Okay, so when we talk about matrix algebra, for instance, which we call matrix algebra, even if it may or may not have all of the properties that we expect for things that are algebras in the formal sense. We might get to that here. Set of invertible 2x2 matrices. Invertible 2x2 matrices with matrix multiplication. So if it's invertible, AB is not equal to BA in general, okay? But the identity matrix multiplied by A, and A times the identity matrix is going to give you A, so it's got that nice property, okay? This is, yeah, there's an identity element. A times A inverse is equal to A inverse times A. Those are both equal to the, did I just say additive? Those are both equal to the multiplicative identity element, the identity matrix here. So we've got that, and it's a group under multiplication, matrix multiplication, even though it's not commutative. So it's not a commutative group, it's not an abelian group, but that seems like a nice property. So I might like to ask for commutativity. So x star y is equal to y star x all the time. That would restrict my attention to things like addition and not subtraction. So addition would maybe be the primary operation, and then I'll just define subtraction as evil addition in some other context where I need subtraction. All right. But here's your definition of an abelian group. So what are the properties that it's going to have? Well, it's closed under whatever operation you just chose. It's commutative, because I'm demanding commutativity now. It's associative. I can move the parentheses around with respect to that operation you defined. And there's an identity element. And because there's an identity element, I also get these inverses here. So I can make myself disappear, I think. There you go. X star y is equal to y star x is equal to I. There we go. Straighten up that background. Keep the production quality high here. All right, much better. So adding the extra property, no big deal. It's just one more property to ask for. But that's a nice step. An abelian group or a commutative group is a nice step. From that, we'll define a ring. So you hear about ring theory, group theory, ring theory, field theory. What's a ring? A ring is an abelian group, a commutative group, with an extra property added in. So instead of just addition, think about addition and multiplication. But here I'm going to call them star and dagger. Okay, so what do they do? I got a group with some additional properties. It's a ring now. It's a set which is closed under two operations, star and dagger. And I'm going to ask for it to be an abelian group under star. Okay, so it's an abelian group under star. Then you add in the second operation, dagger, and I demand that it must be associative under this dagger, this second operation. X dagger y dagger z with parentheses on y dagger z is equal to x dagger y in parentheses dagger z. I'm going to add a new property which I didn't define earlier, distributivity. The operation dagger distributes over star. Well, you can't define distributive until you have two operations. That's why it doesn't show up until now. Look what we've got. X dagger parentheses y star z is equal to x dagger y star x dagger z. So the x essentially goes past the parentheses and looks at the elements inside of the parentheses and then operates on each of them individually. So I say that dagger distributes over the parentheses because I can rewrite this without the parentheses. And if you do some algebra, of course, you'd be moving things when you think of algebra with x's and y's and numbers floating around and trying to solve out some equations, moving things around and doing manipulations, elementary operations to try to solve. There's a lot of that happening. So distributivity is a very important property for algebra in the colloquial sense, building up towards field theory, which is algebra theory, if you want to call it that. And the same thing in reverse here. I've got y star z. So distributivity itself sort of commutes. It works backwards. Y star z dagger x should be y dagger x star y dagger z. Well, this is very abstract. I don't know what the star and the dagger are. So I'm going to go ahead, with your permission, and just rewrite those as addition and multiplication, these two operations that I know and love. And I'll say a ring is a set R, which is closed under two operations. I'm specifying addition and multiplication, although it's more general than that. It could be anything, but addition and multiplication are the ones that normally have these properties. And let's check and make sure. So imagine I'm working with Z, or real numbers if you like. Real numbers are great. They're they're a ring, but they're a little bit more than a ring. So how about this? I've got an abelian group under addition. I want associativity from multiplication so that x times y times z is equal to x times y times z, moving the parentheses here. And you know, with real numbers, that's going to work for multiplication. It's going to work just fine. And I want distributivity. So I want x times parentheses y plus z to be x times y plus x times z. And yeah, for multiplication and addition with real numbers, of course, these things are going to work. They might not work everywhere. Z is a ring with addition and multiplication. Great. Thank goodness. The rational numbers, the real numbers, Q and R, are also rings. There are other things that are rings. Polynomials are a ring. In fact, the polynomial ring is very, very cool because if you take something like a time series course and you talk about moving averages and autoregressive properties, there's this polynomial version of the lag operator that appears there. I used to do this a lot. And inverting that in order to represent a model differently is an important step of the process in order to look at correlograms for things like autoregressive models and try to decipher, looking at the data, what the underlying model might be like. So it's sort of inescapable. We have to talk about polynomial ring theory and try to stretch that into a field in order to really understand at a deep level what's happening in those correlograms, just so I can try to forecast Tesla stock or whatever it might be that I'm trying to analyze in a time series context. It's a really interesting thing that pops up in something that seems like a very, very different field. Well, ring, a very, very different ring, perhaps. Well, polynomials are a ring. If you take a polynomial like this, it has a bunch of coefficients on all of the x's and then x to the power, so it could be x to the 5, x to the 4, x to the 3. Make it x to the 90 if you like. It could be really big numbers here, but you've got x, x squared, x cubed, all of these with coefficients. Add one polynomial to another polynomial, you get a polynomial. And it turns out that they're a group. It's commutative, it's associative. Polynomial multiplication gives you more polynomials. Polynomial multiplication distributes over polynomial addition. It's got all the properties that we want. Okay, so that is true when the coefficients are integers. It is true when the coefficients are rationals or reals as well. So polynomials are a pretty cool almost algebra to work with. And we do have polynomial algebra, and there is a version of this where we can make a field out of them. But in order to do that, I should probably define a field. A field is a set which is closed under two operations. I'm going to go ahead and skip the star and the dagger. Let's just go for addition and multiplication here. A field is a set which is closed under two operations, plus and times, or plus and x, which could be something else, but it has to be an abelian group under the first operation. Without the identity element from the first operation, it has to be an abelian group under the second operation. So why do I omit the identity element from the first thing? Because in the case of addition, the identity element is 0. You add 0 to any number and you get the original number back. Well, making it an abelian group under multiplication would mean that I need to be able to multiply things by 0 and still have an inverse where I can get the original thing back, which seems to imply almost dividing by 0. If you go back and you check that property, you're going to see that, yeah, plugging 0 into that part of the definition is going to be a problem. So we'll ignore the additive identity elements. We don't have to divide by 0. And f without the additive identity element is an abelian group under the second operation. So notice what we've done. It's almost double abelian group or double commutative group. So it's bigger than a ring. It basically works everywhere. The only thing you can't do is divide by 0. And the operation that is sort of like a stand-in for multiplication distributes over addition. So I am going to require distributivity. All right, well, it wasn't in the original definition of an abelian group, so let's make it a little bit better. Make it a little bit more like a ring. We'll require the distributive property holds. That's a field. it's got all of the cool operations. Now, at this point, for real numbers, I can have addition, I can have multiplication, and because it's an abelian group under multiplication, that means there's a multiplicative inverse for every element in the set, which means I can divide. It basically means I can divide. So I can define subtraction as inverse addition. I can define division as inverse multiplication. And I have addition, subtraction, multiplication, division in a field, which I didn't have in a group or necessarily in a ring earlier, although in real numbers, we're used to using all four of those all the time. So a field or an algebra is the version of a set that has all of the properties we're used to on the real number line from arithmetic. This is great. This is where we want to be, right? You don't want to spend all of your time in some set that doesn't have these properties. I'll give you a couple of examples of sets that don't have all of these properties. Polynomials. You can't actually divide by polynomials, but maybe more on that here in a second. There are different ways of defining a field. Like I said, there could be a slightly technical difference in how you define a field versus how you define an algebra, depending on the textbook that you're working with and what they call it and what they're used to. There are multiple ways of achieving the same set of properties, right? So this definition that has 1, 2, and 3 is not the only way to put this thing together. I could have said instead of an abelian group under addition, it's a ring, and then I define some other stuff. All right, fine. Well, in general, sometimes people will say a field is any set that satisfies the field axioms. And these are the field axioms. So it's going to have all of these properties. You've got two operations defined. You can have addition and multiplication, or they can be star and dagger. They can be anything you like that applies to the set you're working with, as long as it satisfies, okay, it needs to be associative. It needs to be commutative. Both of them need to be associative and commutative. Both of them need to be distributive. Both of them need to have an identity element. For addition, it's 0. For multiplication, it's 1. You may want to pause and stare at these for a second to make sure they all make sense, because this is kind of the slide where all of the information is as far as these properties and how they pan out for addition and multiplication. But you're probably looking at it thinking, yep, these do make sense. Invertibility. So the additive inverse of an element we might just call negative that element. It almost defines subtraction, right? And the same thing over here. The multiplicative inverse of an element we might call something like a to the minus 1, or 1 over a would be a good name for it. That looks like division. I just do have to specify that a can't be 0. That would break things over here. So these are the field axioms. It's the other way of defining a field that you might want to look at. Fair enough. So, integers. Z with addition and multiplication. It's not an abelian group under multiplication. Sorry, doesn't quite get there. The multiplicative inverses are not in that set. You can't divide. 1 over 5 is the only way to get 1 back from 5 by multiplication. You multiply it by 1 over 5 and you get 1. But that's not an element of Z, so it's not an abelian group. If I add all of the fractions back to Z and I get the rationals, that's a field. I can also consider irrational numbers and add those back in and just talk about the real numbers. The real numbers are a field. Polynomials are not a field, and it doesn't matter what the coefficients are, whether they're Z or Q or R. Polynomials are not a field because you cannot divide by polynomials and get other polynomials back. At least not all the time. There are some kind of fun special cases. There's this thing that shows up in the time series example I mentioned earlier. Consider 1 over 1 plus x, the multiplicative inverse of 1 plus x. I think we can all agree that that's the multiplicative inverse of 1 plus x. There's this formula for a convergent series, a convergent geometric series, the sum of all the x to the power of I, or often when we're talking about interest rates in economics, this would be r, the sum of all the r to the power of I, and r would be some sort of a fraction or something less than 1 typically. But it's a geometric series, and this thing adds up and happens to be equal to 1 over 1 plus x in the special case where the absolute value of x is less than 1. It is a convergent series. So if you look at what we've got here, I've got a multiplicative inverse of a polynomial on the left. And the thing on the right is x to the I plus x to the, well, it's x to the 0 plus x to the 2, or 1 plus x to the 2 plus x. This is a polynomial. It's a polynomial of infinite order. It goes on forever, but it looks like a polynomial. So if you're willing to consider that, then there are special cases in the polynomial ring, special cases only, but there are special cases in the polynomial ring where you kind of have a multiplicative inverse for a polynomial. And that's very, very interesting and very important in time series. But to abstract from that and just make it work all the time, leave the polynomial ring behind and talk about the field of rational functions, which are any function f of x such that the function can be represented as the ratio of two polynomials, two different polynomials. Well, then I'm adding polynomial division. Take a polynomial, divide it by another polynomial. This thing may not simplify. There may not be a better way to write it. So the result here is not a polynomial itself. We'll call it a rational function. But this will turn the ring of polynomials into a field if we are willing to consider things that look like this. Okay, so that's an upgrade as well. What's next? Sigma fields. Well, let me recap very briefly. A field is just a set that has all of the properties you expect from two operations like addition or multiplication, but sometimes I might ask for some other kind of operations on a different kind of set, and that would be fine as long as it satisfies all of those properties, and we'll call that a field or we'll call that an algebra. Obviously, something is going to be broken here or a little bit different because we are changing the name. Okay, so let's change the name. Let's talk about a sigma field. A sigma field is more or less still a set with all of the properties you might expect, but they're not quite going to look like multiplication and addition. In order to define a sigma field, I need to first make a note about what a power set is. You start with a set. Take an easy set if you want to, like the example that I've got here on the slide, but start by expanding a set into its power set. The power set is the set of all the subsets of the original set. So it's that set, it's half of that set, it's the other half of that set, it's the empty set, it's every possible subset you could define within the original set. We do have this goofy notation that I like to point to for a power set. Sometimes we'll say it is 2 to the power of whatever that set is. So for the set A that we had earlier, it would be 2 to the power of the math calligraphy A. Okay, that's clearly an abuse of notation because that is a set and I can't raise 2 to the power of a set. But the number of elements in that set, in the power set, there will be an element of the power set that either does or doesn't contain the first element of the original set. There will be one that does and one that doesn't contain the second element of the original set for each of the two possibilities with respect to the first element. So two possibilities for the first element, and there will be four possibilities, two elements in the original set. And then if I look at the third element in the original set, the power set is going to have a subset that does and a subset that doesn't contain the third element in the original set for each of the possibilities that I just listed with respect to the first two elements of the original set. So for every element in the original set, x, the number of possibilities in the power set doubles. So the cardinality of the power set, the number of things in there, is equal to 2 to the power of the number of things in the original set. So if you see this notation, it means something. It corresponds to the size of the power set, and somebody decided that this was an okay way to write the power set of x. But as you see, I've written it out in actual words here, power set of x, just to be clear what we're talking about there. And I'm also going to use the letter p for something else here in the future. But that would be the alternative way of denoting power set is p of x. And that looks like probability, so I'm not going to do that here. But here's an example. Power set is just the subset of the set of all subsets of x, including the goofy trivial subsets like the whole thing of x and nothing. So if X is the set north-south that I mentioned earlier, the power set of that, let's see, subsets. Original X had north and south in it. So north would be a subset, south would be a subset, north and south would be a subset, and then the empty set down here. Of course, the original set had two elements, so 2 to the power of 2 says 4, 2 squared is 4. There should be 4 things here. If I write them all out and I have less than 4 elements, that means I didn't think of something. If there were 3 elements here, north, south, east, then I should have 2 to the power of 3 possible combinations of those into subsets, including the trivial subsets that include all of them and none of them. So this is the power set of this silly little set north-south. Nice, not bad, easy. But, okay, let's make a sigma field out of a power set. Notice what I did. I took the original set X, which could have been something like Z, the integers, or R, the real numbers. I took that and I defined it as something much, much bigger. Not the original set, but every possible subset of the original set. So this is actually huge. In this case, where there were only 2 elements in the original set, it became 4. But if X is the real number line, and I want to talk about the set of all possible subsets of the real number line, that is mind-bogglingly large. How many different subsets you could define on the real number line. So the power set is big. And I'm going to define something like a field in that power set, in that really big set of all the combinations of subsets. So for a original set X, any subset of the power set, it doesn't have to be all of the power set, but it's a set of subsets of X. Any subset, we'll call it sigma, is called a sigma field if it contains the original X. That's going to be important. It needs to contain the whole thing. It needs to be closed under 2 different operations. The complement we defined earlier, inherited from X. So if there's some subset in sigma, then the complement to that subset needs to be in sigma. I'll give you an example. All right, north. What is the complement to north here? Everything in X that isn't north would be south. So the complement to north is south, and in the power set of X, guess what? South is there. So the power set does contain that complement. I could have a subset of these things, and as long as it's closed under complement, then we're kind of okay from having the nice properties that resemble a field. Notice all I'm asking for is closure under that operation. And I'm going to ask for closure under another operation as well, countable unions. Okay, so if I have subsets in sigma, A1, A2, A3, and I make the union of those subset, which is A1 or A2 or A3 in plain language, that combination, that union, needs to be in sigma as well. Back to the easy example. North was a subset of X, south was a subset of X. The obvious union of north and south would be a set that contains both north and south, which in fact is the entirety of the original X that I defined. It's this set north and south in the set. So the union of north and south needs to be here, and guess what it is? It's right there. It's in the power set. So I can combine different elements of this sigma, whatever it is, some subset of the power set, not necessarily the whole thing, and as long as it's closed under complement and countable unions of things, you can imagine a scenario where you have an infinite union. You write it out as an infinite list of things that you add together. As long as it's countable, as long as you can list them, it needs to be closed. And that's this. All right. Okay. That's it. That's a sigma field. All right. Okay. Well, back to here. So first of all, if X is in sigma, we're good. If it's closed under complement operation, we need that. And if it's closed under countable unions. So for this set, you can check them all. The original is there. It's closed under complements. pick any one of these, pause the video if you want, pick any one of these and verify that its complement is there, or pick any subset of these and verify that the complement is there. The complement to north-south would be an empty set. The complement to the empty set would be the entire original set, north-south. So yeah, everything is there. And the same thing with unions. If I take south, the union of south with the empty set is south, which was there. The union of north with the empty set is north, which is there. The union of north with south is this whole original thing, which is there. So it's closed under both of these. Beautiful. Kind of just said that. So the power set of X, okay, oh, that's the big one, all right? This is the power set itself. But just to clarify, a sigma field is any set that has these properties within the power set. I'll give you the easy one and take out north and take out south from here. Scratch this, scratch that, and I'll define sigma as a subset of the power set that only includes the original set and the empty set. So this would be a trivial sigma field, just the whole original set and the null set, the empty set. And it's easy to check that this is closed under unions because x plus nothing is x. And it's easy to check that this is closed under complement because the complement to x is nothing, and the complement to nothing is the entire original x. So yeah, that would technically be a sigma field as well. And if I build something that's more complicated than just north and south, if I talk about all of the things that could come from rolling a six-sided die, 1, 2, 3, 4, 5, 6, that power set is going to be large, 2 to the power of 6 elements, and I could probably come up with a scenario where I say, okay, well, what about just the even numbers or just the odd numbers? And that would define a very, very simple power set. That's power set. Sigma field, which would be a strict subset of the power set. Okay. All of those would be sigma fields. Any subset of the power set that follows these rules we will call a sigma field. It follows, by the way, under 2 and 3, you can prove that the empty set is also in there. So if I say x is in there and 2 and 3 hold, I can prove that the empty set is also in there, and that's sort of like the identity element under countable unions. And it's also sort of like the inverse of the original thing under complements, and so it does sort of look like something that might resemble a ring or a field. We usually use this in the context of probability. So a probability space is a combination of three things. We'll call it a mathematical triplet. Probability space is a set, good old X, whatever that set is that you started off with. We'll call it the sample space, and that's the list of all the things that can happen. For a six-sided die, it's 1, 2, 3, 4, 5, and 6. But that's not good enough to define probability, because I don't need to know the probability of 1, 2, 3, 4, 5, or 6 individually. I want to be able to consider a universe where I define events on combinations of those, subsets of the power set. I want to be able to ask, what is the probability that a six-sided die comes up with an even number? I want to be able to ask, what is the probability that a six-sided die comes up with a 1 or a 4? I want to be able to ask additional questions like that. So we'll define the power set, everything that could possibly happen, all the combinations of these outcomes. And sometimes we could be interested in a smaller subset than that. But I'll define the power set, and from that I will build a sigma field denoting events. So every possible combination of 1, 2, 3, 4, 5, 6, maybe nothing, maybe the whole list, in my sigma field is something that can have a probability assigned to it. So the probability that a six-sided die comes up 1 or 2 is going to be 1 out of 3. 1 or 2, right, that set 1, 2 would be the union of 1 and 2. So my probability function that I define needs to be able to incorporate the idea that 1 and 2 can go together into a new event. Hence, I need the sigma field on the original set and not just the original set. Can you define a sigma field on the real number line? Yes, it's going to be ridiculously large, but of course you can do it. All right, and in a probability space, I've got an original set, I've got a sigma field to go with it, and I define the probability function or measure, which is kind of a function. It's a mapping from the sigma field to the unit interval, 0 to 1. So that mapping tells me the probability of these events, and probability is just defined out of 1. The probability of an event has to be at least 0. There are events that never happen. Like if I toss a coin, what's the probability that it comes up heads and tails? Shouldn't do that. It really shouldn't do that. But a probability measure has to satisfy some axioms of its own that come from Kolmogorov. So thanks to Kolmogorov for making probability an axiomatic, proper element of what we consider to be mathematics, and not just statistics. But a probability measure has to have this, for instance, the probability of a union. It can be a countably infinite union of disjoint sets, has to be the sum of the probabilities of each of those things. So in the six-sided die case, the die comes up with a 1 a sixth of the time. It comes up with a 2 a sixth of the time. And the 1 and the 2 are disjoint. A die cannot come up with a 1 and a 2. So this rule says that the probability of 1 or 2 needs to be equal to the probability of 1 plus the probability of 2. Here's the probability of 1 or 2. Here it has to be equal to the probability of 1 plus the probability of 2. And it is, because they're disjoint. The probability that a die comes up with a 1 or a 2 is 1 out of 3. So it works. And the probability that anything at all happens, the probability of the entire original set, 1, 2, 3, 4, 5, and 6, the probability that a six-sided die comes up with a 1, a 2, a 3, a 4, a 5, or a 6 has to be 1. All right, so these are rules for what constitutes a probability measure. But a probability space is just a list of the original set, all of the events you can define as combinations of those original outcomes in the original set, 1, 2, 3, 4, 5, 6, or north, south. And then the probability function takes elements of the sigma field as arguments in order to return that number that makes sense for how often that event happens. But the event can be defined as combinations of outcomes. So that is why we need the sigma field with those fun operations. In this case, all right, north-south, easy peasy. It's a pretty simple sigma field on a power set to go ahead and write out. You might think about flipping that into heads and tails. And then you've got your favorite fair coin that you can toss. Or maybe it's not a fair coin. Maybe you've got a coin that is heads on both sides, and you use it to trick people. Please don't. But this is very easy. If it's a fair coin, I can define the probability of any of these events. What is the probability that it comes up? Because this is like a trivial sigma field. It's the entire power set. What's the probability that it comes up heads? Well, 0.5. What's the probability that it comes up tails? 0.5. What is the probability that it comes up the union of heads and tails? Heads or tails, which I'd write as this set of all of the events that I will consider, or all of the outcomes that I will consider as this event. The probability that it comes up heads or tails would be the probability of this event, which is going to be 1. And then the probability that it comes up with nothing at all. It vanishes into space. Well, that's the probability of the empty set should be 0. Of course, it's the complement to the entire original set, which had measure 1. So if heads or tails always happens, then the empty set should never happen. That would be probability 0. Easy, very easy. Okay. But because we have a sigma field here and it's closed under complements and finite countable or possibly infinite countable unions, I can say all of the logical things that make sense. I can say, what is the probability of heads or tails? Well, write that out. The probability of heads or tails. The union of heads and tails is this event. Heads, tails, either of those. So that's the probability of the original set, which has to be 1 by definition. Okay. I could also say, what is the probability that it's neither heads nor tails? That means not heads and not tails. So here's not heads. It's the complement to heads. Anything that isn't heads would count as not heads. And here's tails. It's the not tails. It's the complement to tails. So anything that is not tails would count as that event. And this isn't a union. This is an intersection. All right, so the intersection of not heads and not tails. And I can go back to my list and say, okay, what would that be if it's not heads and it's not tails? All right, so not heads would mean tails, and not tails would mean heads from the original set of just heads and tails. And it has to be the intersection of both heads and tails. So heads is a singleton. It's only one object, heads. And tails is also a singleton. It's only one object, tails. If these were big sets in the event, and I talked about the intersection, there could be some overlap between those sets. There could be a six-sided die comes up 1 to 4, or a six-sided die comes up 3 to 6. Well, 3 and 4 are in both of those sets. There would be an intersection. But here there's no intersection between heads and tails because they're singletons. They don't overlap anything except themselves and supersets of themselves. So the intersection between this, which is just tails, and this, which is just heads, is an empty set, and the probability of the empty set is 0. So notice what we did there. I've got the union up here because the sigma field is closed under unions. Here I used an intersection, which is also fine, and being closed under complements and unions is enough, just like knowing how addition works is enough to build subtraction once you have those other nice properties. In a sigma field, knowing how unions and complements work is enough to build intersections. So I didn't need to define intersections up here and say a sigma field also has to be closed under an the sigma field having properties 1, 2, and 3 is enough that I can prove that I can then define intersections just using these properties, just like I can define subtraction using addition in something like a ring or a field. Well, beautiful. That's wonderful. So I've got intersections here as well. There are things to be said about, for instance, distributivity looking like De Morgan's laws, which we also have. And then a sigma field is a set with two operations that are closed and kind of imply some other operations that you can define easily, and maybe even something like an inverse or an identity element. And distributivity in this context, De Morgan's laws, it does imply both unions. They sort of map to intersections in De Morgan's laws. It's not in the slides here, but it starts to look like a regular definition of a field with a little bit of extra fuss to it once we get into this stuff about sets. So I hope this video was helpful to anybody who's interested in group theory, ring theory, field theory, or sigma fields and probability spaces. Of course, I've only given you the simplest examples here. Heads and tails on a fair coin is as easy as it gets, but that's the idea. As far as groups, rings, fields, and even sigma fields are concerned, they're just sets of elements that have the nice operations you would expect those sets to have. And I can give you some examples of sets that don't have some of those operations or don't behave particularly well. They don't satisfy all of the properties that you might want for certain operations to have in an algebra environment. But groups, rings, fields, the nice one, and sigma fields behave as you might hope them to based on those properties. So that's it. It's hopefully easier than you thought it might be. Thanks for watching.